says, maybe you shouldn't have said that to me. That's maybe one of those keep to yourself thoughts. I don't, just a thought. No judgment. But.
I mean, like, no, seriously though, like, so my nose itches, and
Have you ever used there's a machine that shoots water up one nostril and vacuums?
I've seen that. I want to use it so bad.
I have one of those. It's
Does it hurt?
no. I wish it was stronger. I wish it just really was like a spoon.
But does it get a lot out? So
Not as much as you'd think.
not as much as the commercials.
I don't know. Anyways. Yeah, I think it seems a lot better than it is. That's my opinion. All right. So skew. I think we talked about skew before, where we talked about outliers, right? What do outliers do to data?
Pulls it up or down.
Pulls it up or down, right? So I want to talk about skew real quick without a picture. So if the outlier, say if the outlier is left, meaning that it's smaller than the data, what is it going to do?
And make it, wait, if it's small, then pull it down.
It'd pull it down, right? It would pull it which way? It would pull it left, right? And I'm not trying to be tricky here. And if it was right, meaning that was bigger than the data set, it would pull it right. I honestly was looking at this yesterday and I was like, wow, I totally had something backwards in my brain for this next part. We wanted, looking at this first one, which way is this skewed?
Or right?
It's skewed left. These are the outliers, right? Those are the guys that are kind of off, right? Most of the data is here. Would you agree? Like if I drew like where most of my data is, it's mostly here. So the outlier is here. So this skews, this guy is pulling it left. They say it's based on the tail. They call these the tails. Which means this guy is skewed how? Right. Because of most of the data is here, and then these are my outliers that are pulling at the tail. And then we have symmetric, which means it's like a perfect curve. Some of this we've already seen, but we just got to talk about it in this other way. So in this first one, which one's bigger, the mean or the median?
Probably the median.
The median would be bigger. Okay? Because the median doesn't get affected by outliers, but the mean does get pulled down when the outliers are over here. The mean on this one is getting pulled how? Up. So that means it's greater.
Oh, wait, is that just how it works?
Yeah.
Wait, I'm trying to do number one.
And then in perfectly symmetric data, the mean and the median are what? Equal. And they might even be just really close, right? So on this one, it does look like it's perfect, but if it's just a little bit off, they'll be super close to each other. One might be 90 and the other one could be like 91. So super close, but almost equal. If we have spread out data, the MAD is spread out, or close data, which one's going to be a greater MAD? Spread out. So spread out MAD is bigger than a non-spread out MAD. We have this concept called standard deviation. Standard deviation means that there's a way of calculating how close you are to the mean, right? So One example is light bulbs. Okay, they say these light bulbs last 1,000 hours. And you call them up and you say, my light bulb lasted 950 hours. I want my money back. They'll say, well, it was within this one standard deviation, so we won't do that. Okay. You call them up and say, I just bought these light bulbs and they last 10 hours. Well, that's way outside, right? So it's a measurement, it's a unit for how close you were. Okay. In testing, they'll talk about how many deviations are you above or below. So you guys all tested above the deviation, probably 2 deviations above, and that's why you're in this class. Okay. Say again?
What's that mean? Oh, is everyone special?
Yes, you are. I mean, you're taking a high school class in middle school. That means you're special. And if no one's told you, you are special, Tommy. You're welcome.
Wait, what is deviation?
So it's a unit, right? So it's a number that's going to tell you, okay, how close we are. Okay, so I've talked enough about it. It's MAD just tells you how spread out something is. Deviation gives you more details. It's a unit of that. Okay, so let's calculate this. First off, this symbol here, anyone know what X with the bar on top means? Anyone want to guess?
Repeated.
No? That's a good guess. Anybody want to guess?
Average of given data.
It's the average.
Oh.
It's literally on there. That means average. Anytime you see an X with a bar on it. So stat people got so tired of writing the word mean that they came up with a symbol. This just means average, right?
I think they make a symbol for deviation.
They do have one.
Oh, they do?
Yeah. So then this right here, this looks a lot like what we were doing yesterday where we were trying to figure out the MAD. Okay. So if you find the average of this, that is the MAD. But then for standard deviation, we're going to do something with it. So anyways, we need the average. Anything we can do in Desmos to speed up our time, I think we should do in this chapter. I'm going to use the state calculator, which pretty much has almost every other feature. And I really hope at this point we're all really good at using this 18, 25, 18, 10, 17, 15, 18, 15. Did I miss any points? So I need to know the average, also called the mean. So I go down here and I click on that function and I click on stats and I need to know mean of X1. And it tells me it's 17. So that means for all of these points, it's 17. So now I need to know the difference between the mean and the point. So 1. And this doesn't say to make it positive, right? But once I square that number, what's going to happen to it? It's going to be positive. So I'm going to just kind of ignore the positive negatives because it doesn't really matter. 8, 1, 7, 0, 2, 1, 2. If I take the average of these, what is that? It's the MAD. Okay. So if I take the average of this, that's the MAD. Just for funsies, let's add that on here. So I'm going to make another chart. Some you can put it in here, but I kind of like just adding new tables just so I don't make mistakes. 1, 8, 1, 7, 0, 2, 1, 2. Do I need to include that 2 or that 0? I mean, yes, because this average means we're going to divide by that. And then I can do a mean of X2. It tells me it's 2.75. What data point do you think is making that so large?
7 and 8.
Yeah, these 2 points right here, 25 and 10. Okay, good. So now I'm supposed to square these numbers. 164, 149, 0, 4, 1, 4. The variance, which is this, so it's like a 0 with a little hat. The variance, which is a 0 with a hat squared, is the average of these. Okay. Wait, hold on a second. Am I messing this up? Oh no, that's right. Okay. The variance. So now here's the weird thing about this. We have two different types of variances. We have a sample type and we have a population type. What's the only difference between those two equations? The denominator. Okay. So we have two types of variances. We have a sample type and then we have a population type. Okay. The sample type, we're going to divide by how many there are minus 1. The population, we're going to just divide by how many there are. Okay. N always represents how many. How many points. Okay. So I'm going to go over here and I'm going to, actually I just need to add these up. I think our calculator will add them up. Total. So if I go over here and I go a list and I want to add them up, so my numbers are 164, 149, 0, 4, 1, 4. Did I miss anything? I want to total those. The total of x2 tells me it's 22. Math can't be right. X3, and I always do that. 124. Better. So this equals 124. So that means the sample variance is the one we divide by 1, 2, 3, 4, 5, 6, 7, 8 minus 1. So I'm going to divide by 7. I get 17.7. The other one I'm going to divide by 8, right? 15.5. These are the variances. These are not the standard deviation. The standard deviation is just the little guy without the squared. How do you get rid of a squared? Square root. So we have the standard deviation, the sample kind. We have the standard deviation, the population kind. So all I got to do now is go square root of 15.5, and I get that one is 3.937, and then standard or square root of the sample is 4.209. Okay. The population one is the average of those numbers, right? Where the sample one is kind of like the average, but you take one of the items away. So that's saying that if I asked you if you were within one deviation is 4.2, depending on which of these we're talking about, or 3.9. Okay. So how close were you to the average? Well, our average was 17, and one deviation is less than 3.9 less or 3.9 more.